All right, this is essay number 1 for Unit 4, and we're talking about the kidney. This whole essay question, we're just going to talk about the kidney. So the kidney, it's a filter for the body, helps get rid of waste, and it can also help balance pH. It can help with dehydration and blood pressure, does lots of cool things. First of all, with the anatomy of the kidney, we have 2 kidneys. This is the main part of the kidney, and kind of like a kidney bean. And it kind of what happens is there's blood vessels that go into this part of the kidney, and those blood vessels will filter out certain things into the kidney, and it'll kind of leave it up to the kidney to keep those things or get rid of them. And sometimes the blood, it will go back into the blood, and sometimes the blood will put it back into the kidney at a later part, and then eventually it's going to get excreted or disposed of through the urinary tract. And so within the kidney, well, I guess not within, but we have the ureter that goes up to, because that's where the stuff drains from the kidney, it's our pee, but it goes up to the major calyx, and the major calyx will then divide into smaller calyx called minor calyxes, and they are kind of like a funnel for these different, they're called renal pyramids, and inside of these renal pyramids is where we have nephrons. And these nephrons is where it's very small, and they make up the renal pyramid. And what happens is blood will flow in these nephrons, and as blood flows through, certain things will filter out of the blood and go into this part of the nephron. And as it moves through the nephron, it will reabsorb into the blood, stuff will get secreted in, and eventually it will get excreted. But I like to kind of show the big picture. So I'll go back over it at the end to kind of bring it back all together, but we have a nephron. It's located in this renal pyramid, and there's a bunch of these nephrons in there, and they'll essentially collect fluid, and a bunch of these will be in this pyramid. They'll be letting out fluid. It'll be collected into what's called the renal papilla, and that will then go into the minor calyx, and it will all kind of start merging together into the major, and then we'll feed it down into the ureter. Eventually it'll go down to the bladder, and then it will be excreted from there. But yeah, on the outer portion of the kidney, we have the cortex. The inner portion, kind of all these pyramids, that's the medulla. Then you get into the calyx, but not super detailed, but enough to where I think we'll cover what we need to cover. And then before we jump to the actual nephron, I want to come over here and look at this part. So this is like the function of the kidney and the nephron. So, like I said, I didn't show it super well. I'll go back over here and show it real quick. But here with the kidney, you have certain blood vessels coming in. You have the renal artery coming in, and then the I think it's the renal vein will then come out, and it will break down into arterioles and then into capillaries within different parts of the kidney, especially where we're talking with the nephron. It's in the more so in the renal pyramids. But for this part right here, we have a blood vessel coming in, and eventually it's going to turn into the afferent arteriole. And then eventually it's going to get to a point where where it hits the nephron, and And in the nephron, one of the main parts is the glomerulus, or the glomerular capillary. And this is where filtration happens. There's a pressure within this capillary, and the pressure pushes fluid through the capillary into this part right here, which is called the Bowman's capsule. And it will filter it through, it'll go through a filtration process through the membrane, and it will be into the tubular, or the tubule. And then after the glomerulus, it will continue to the efferent arteriole. It'll move down to the peritubular capillaries. That's what this is, peritubular capillaries. And like we said, there's filtration, but then as things get filtered, they can also get reabsorbed back into the bloodstream. And things in the blood can be secreted back into the tubule, or the collecting duct, or the collecting tube, or tubule. And then eventually, whatever's left in will be excreted, like we talked about. Will go into, I guess we have it drawn over here, go lead into the collecting duct and duct into the renal papillae, can't remember, I think it's the papilla. It'll be put into there, and then from there, it will go into the minor calyx, and then the major calyx, and then it'll make its way into the ureter, and then into the bladder. But yeah, these are the important processes, or parts of what the kidney does with the nephron. It does filtration, reabsorption from the tubule into the blood. Then it can do from the blood and back into the tubule, or to the tubule, secretion, and then whatever's left will be excreted. And so we get in more to the, let's see, that's better. Get more into the nephron. So with a nephron, there's two parts of it that aren't quite identical, but very similar. And one of them is called the cortical nephron, and one of them is called the juxtamedular nephron, and that's this one over here. I didn't write it, but this is the juxtamedular. And these 2 points right here, kind of the ball, that is called Bowman's capsule. And that's what we were talking about kind of over here, where we have this, the glomerulus, or the glomerulus capillary. And that's kind of surrounded by, or encapsulated by Bowman's capsule. And stuff will come out through like the membrane of the blood vessel, through the capillaries, and will kind of drain into Bowman's capsule. And that's what will get filtered through, but then it will, that's what kind of feeds it into the rest of the tubule. And so that's what's happening right here. We have the glomerulus, we have the afferent arteriole coming in, it hits the glomerulus, and then we have the efferent arteriole coming back out, and it will feed through the rest of the nephron. But let me think here. There's something I wanted to say, but I kind of forgot what it was. That's okay. But yeah, let's just start at Bowman's capsule. So like we said, through the blood, it gets filtered through the membrane, and it enters into Bowman's capsule, and it comes into the tubule. And it moves down the tubule, and there's different sections of the tubule. The first section is the proximal convoluted tubule, and that's this section up here, that first section right after Bowman's capsule. And then right after the proximal convoluted tubule, we have the proximal straight tubule. And that's where most of the reabsorption of water and a few different elements, or not elements, but molecules. We'll talk about that more in just a second down over here. But then we have the descending tubule, which is still, what's the word I'm looking for? It still allows water to pass through. But then we get down to where we're not descending anymore, but we kind of curve back up, and this loop right here is called the loop of Henle. And as we start coming back up, we have the ascending tubule, because this is the direction of the flow. So descending loop of Henle, ascending tubule. Then we get to the late, well, I guess right here we have something called the macula densa, and that's an important part we'll talk about more. And that's like the first part, or kind of the part, so you can say it's kind of like the first part of the late distal tubule, or it's just right in between the ascending and late distal tubule. And yeah, right after that we have the late distal tubule, and then that comes down into the collecting tubule, which is right here, and it makes its way down to the collecting duct, and then to the renal papilla. And yeah, just the exact same on this side. The only difference for the juxtamedullary is its loop is a lot longer. And I'm trying to remember exactly, I think the cortical nephron is a lot more abundant within the kidney. And for humans, we do have the juxtamedullary nephron, but it's just a lot more, it's not as common, it's not as present as the cortical. And so it still exists, but there's a lot, the majority is these cortical ones, but we do have these juxtamedullary. And yeah, the things that make these different is they have a lot longer of a tubule. The loop goes down a lot further. But I guess something to mention too, as we talked about the kidney, kind of the layers of it. The outer layer, we have the cortex. This kind of more inner layer, we have the medulla. And then we have like a, kind of like, I guess you could say the cortex. Then we have the outer medulla, inner medulla. So those are kind of the layers we want to focus on with this right here. And so, as you can see, this top part, where Bowman's capsule is, that's within the cortex region. And then more of the midsection, kind of where the loop of Henle is, and descending, ascending tubule. That's more where we have the outer medulla. And then down here, where we have the loop of Henle for the juxtamedullary, that's more the inner medulla. Because that's filtering down into the kidney, it's going to make its way to the major calyx and then out of the kidney into the ureter, not the uterus. And kind of back with the blood vessels. So again, we have the afferent arteriole. It goes to the glomerulus, or the glomerulus capillary. And from there it goes to the efferent arteriole, and then it feeds down and feeds the this section of the nephron, and that's the peritubular capillaries, and that pretty much was what covers the blood vessels for the cortical nephron. But like we talked about the juxtamedullary nephron, it goes a lot further down, and so we have these blood vessels that come down to feed through here, and that's the vasa recta. So that's specific to the juxtamedullary nephron. And so that's it's kind of all I have for here. Kind of gives us a simple breakdown of the kidney and the nephron, and we'll continue to go into more detail. Trying to think what I want to go into next. Let me read the essay question. Yeah, let's jump over here and talk about filtration. You might want to bring it over here. That should be good. Covers a lot. Okay. So in this part, I want to talk about, let me see. Yeah, let's talk about, Yeah, let's talk about filtration first, kind of the components that go into that. So for filtration, there's, like we talked about, we have the arterial, the glomerulus, or the glomerular capillary, and that's how we're getting fluid to come into Bowman's capsule. It's coming from that capillary, coming from the blood. And let's talk about pressures first. Yeah, let's talk about that, that's good. So, I have a little cheat sheet right here. It's purple too. Actually, let's not use red, let's use green. Okay. So, we know we're having a net filtration pressure because fluid's leaking into Bowman's capsule. Again, this part right here is Bowman's capsule. That's what's capturing the fluid, or the filtrate. And so we know there's a pressure from the glomerulus that's pushing into Bowman's capsule. So if there wasn't, if there is a pressure going that way, then there would be no fluid coming out of the capillaries. But since fluid's coming from the capillaries into Bowman's capsule, we know there's a pressure that's pushing that fluid out through the membrane into Bowman's capsule. And there's a net filtration pressure, and we're going to talk about what makes up that pressure. That net filtration pressure is, I believe it's 10 millimeters of mercury going out. But we're going to talk about what creates that 10 millimeters of mercury going out. When I say out, I mean out of the capillary of the glomerulus into Bowman's capsule. So inside of Bowman's capsule, we have a hydrostatic pressure for the glomerulus, and that's pushing out down into Bowman's capsule at 50 millimeters of mercury. And if you remember when we talked about, what was it? It was just like a unit or two ago, we talked about, I think it was just capillary exchange, and we talked about hydrostatic pressure, B cop, C cop, and what was the last one? Interstitial fluid pressure, I think it was. Kind of the similar thing going on over here. Hydrostatic pressure, this is just a pressure that's coming from the blood. Kind of like if you have a high blood pressure, it's going to cause a high hydrostatic pressure because we have a lot of fluid in that small area, or in that area. So that high pressure is going to push things out. And so that's usually at 50 millimeters of mercury. And then also, that's the only one we have coming out. Coming back in, we have something called, I'm going to call it B-COP again. And this is the blood colloid osmotic pressure. And I think in the book it had a different name. It was like oncotic something pressure. I can't remember. But basically what it is, we have like proteins, we have solutes within the blood, and it's based off osmolarity. And so if we have something if the blood has more solutes per liter, then the solutes can't cross the membrane, but water is going across the membrane because it wants to have an even osmotic pressure throughout, I guess maybe you could say the system. It's going to move to an area of high concentration to low concentration, but since the concentrations can't move, water is going to be the thing that's moving. That's what osmosis is. So it's going to want to even it out. And so we're going to have like proteins and different things in here that are a higher concentration than the Bowman's capsule. So that's going to cause a pressure to go in, and that was 30 millimeters of mercury. And so hopefully I can explain it a little more simple. There's high osmolarity inside the blood, and there's a lower osmolarity, lower amount of solutes out in Bowman's capsule. And so water is going to move into the capillary to even that out, to lower the osmolarity in Bowman's capsule. Sorry, not Bowman's capsule, in the capillary. But something with these two is, right now I'm kind of talking about all of them individually. And so when we're talking about hydrostatic pressure, we're acting like that's the only pressure. When I'm talking about BCOP, we're acting like that's the only pressure going on. But then in the end, we'll combine them all. And then the last one is actually in Bowman's capsule, we have a hydrostatic pressure, and that is for Bowman's capsule, and that's going also up into the glomerulus, and that one I believe is 10. And all of these kind of have different numbers. Like this could be like 50 to 55. This could be, I think, with like 28 to 30. This could be like 10 to 15. But we're just gonna go off these numbers because they're simple and they're still accurate, at least from what the book says. And so we have these different pressures, and you can also call this capsule pressure. We'll call it the hydrostatic pressure from the Bowman's capsule or whatever. But yeah, the pressure's going in, BCOP bringing pressure in, hydrostatic pressure from the Bowman's capsule pushing pressure in, but then we have hydrostatic pressure that's pushing out from the capillary into Bowman's capsule. And so let's kind of add up these numbers. We have 50 out for the hydrostatic pressure coming from the glomerulus. We have 30 going in for BCOP, that's within the glomerulus. And then lastly, we have 10 going in from the hydrostatic pressure from the Bowman's capsule. And if we add all of this up, we get 50 minus 30 minus 10. That gives us 10. So that's how we get the 10 out. It's because we have so you add these two up, these two, it's 40 in. We take 50 minus 40, we get 10. Which one was the bigger number? Out was, so it's 10 out. And so that's what makes this filtration possible. And we're going to talk about more why that pressure, that hydrostatic pressure, or that net filtration pressure is so important. And there's different things that can affect it. One of them is like low or high blood pressure. That can change this filtration. Something called the GFR, the glomerular filtration rate. And we want to keep that glomerular filtration rate within its healthy range. And there's different things we can do to change that and regulate that to keep it good when it's not good. But since we talked a little about GFR, so GFR, like I just said, glomerular filtration rate. So it's just the rate at which fluid is being filtered through this area, through this membrane into Bowman's capsule. And I honestly can't remember exactly what it is. Let's see. I think it's like milliliters per minute or something. GFR. Yeah, it's usually milliliters per minute. And we're going to talk about how they measure that real quick. And that's something that's a tool that's used, or let's say strategy, but a technique. That's what I was looking for. A technique to measure GFR, something called clearance. Right there. Okay, so we know fluids being filtered through here, but how do we measure that? The way we measure that is something called clearance. And let's see. Clearance is measuring, should have written this down. Clearance is measuring how much of a substance is being cleared from the plasma within the blood, or how much a substance is being cleared from the blood through the nephrons. So for example, let's say we have, we're gonna use this picture here. Let's say we have a substance come through and it's in the blood and it's 125 milliliters. Let's say it's 125. I can't remember what the exact, I think it's like 125 milligrams. It goes through, it gets filtered, but it doesn't get reabsorbed. No more of it gets secreted in, and all of it gets excreted. So 100% gets excreted. So we end up with $125, 125 milliliters, or 125 milligrams in our per milliliter in our cup. Or maybe it's grams. I think it's grams per milliliter. What? No, it's probably milligrams. I don't know. But we started with 125, went through, didn't get reabsorbed, didn't get more secreted, didn't get metabolized, multiplied. 100% was able to filter through. It got down and it made it into the cup. The same amount that was up here made it into the cup. So that means, like we talked about with clearance, clearance is telling us the amount that got cleared from the blood. So 125 grams got cleared from the blood because all of it came out, none of it went back into the blood, none of it stayed and went through, all of it came out, none of it went back in, no more came in. 125 grams per milliliter, or 125 milligrams per milliliter was cleared from the blood. None of it's in the blood. So what I'm trying to get at here is if we have a substance that is able to do what I just talked about, make it through 100% without being reabsorbed or more to be secreted in or metabolized or pretty much taken away or multiplied, and it's able to be freely filtered, all of it's able to be filtered through here, and we get this, that's going to tell us that's going to give us an accurate reading of how much is what our glomerular filtration rate is. That's going to tell us how much is being filtered through the glomerulus and if it's functioning properly, because it's important to know. I know this is kind of all over, but this is helping me learn it. So we talked about we need a substance that meets this qualification. It needs to not be reabsorbed, meaning once it gets filtered, well, first of all, it needs to be freely filtered. So it needs to be small, not charged. It needs to be able to make it through this membrane, no problem. 100% of it needs to be able to make it through here and ended up in Bowman's capsule. So that's what a substance called inulin can do. Also creatinine. Creatinine is found naturally within the blood, and inulin is something that you can give to perform this test. But I think now they usually just use creatinine because it's naturally found within the blood. But, so, small, no charge, freely filtered. That's what we needed to do. 100% of it that we needed to came through the blood, now it's inside of the tubule. We also need it to not be reabsorbed, so to not to come back out and enter the bloodstream. We need it to stay in the tubule. We also need it that no more is going to be secreted in. It's not going to be added to. We also need to make sure it's not going to be eaten up. It's not going to be metabolized. And we also need to make sure it's not going to self-multiply or something like that. So we just need it to stay consistent throughout the tubule. And as it moves through the tubule, it'll eventually be peed out because it's not secreted, it's not reabsorbed, it's going to be excreted, and we're going to end up with that in our cup. And then we measure our cup, we're going to say, oh hey, that was the same exact amount that we had in the blood, and now it came all the way through, and now we have that amount in the cup. And it's still that 125. So now we know what our glomerular filtration rate is. Because if we're not filtering stuff as fast, it's not filtering stuff, it's not good. If we're filtering stuff way too fast, there's too much, it's not good either. And so inulin, creatinine, there are good solutes or substances for that. Let me kind of recap. The glomerular filtration rate is the rate that stuff is being filtered through this membrane. Clearance is a technique we use to measure glomerular filtration rate. And that gives us a number of how much of a substance was cleared from the blood. And we use this fancy formula. It's the concentration, or no, that's clearance of the substance, that equals the concentration of the substance, or the measurement of the substance in the pee cup, multiplied by the volume, how many milliliters per minute was measured. So like if you're keeping track of someone's pee for a whole hour, and let's say, I don't know what a number, how much someone would pee per hour or come out of the urinary tract per hour, but let's say it's 25 milliliters, we'll have 25 milliliters. Well, it's 25 milliliters divided by 60. That would give us whatever that is per minute. Or let's just say it's 60 milliliters. Be 1 milliliter per minute. P of X, that is the concentration of the substance in the plasma or in the blood. So we multiply those and divide it by that, and it gives us our clearance number. And over here, like inulin, go through a process like that, you should get 125 milliliters per minute. And that's going to match our GFR. Another one is glucose. Glucose is going to be filtered through, and glucose, we'll talk about it more over here, but should be 100% reabsorbed in the proximal convoluted tubule. So 100% should be taken back into the blood. So, like for this case, it's 0. So 0 milliliters per minute was cleared from the blood or the plasma. Because let's say we had 100 grams per milliliter of glucose. Sounds so high. It's supposed to be milligrams. But we're supposed to have 100 glucose filtered through. The clearance is 0. That means 0 got cleared from the blood. So that means all of it got reabsorbed. If any of it got cleared from the blood, it would make its way down into the cup. But in this case, 100% is being reabsorbed, 100% is being pushed back into the blood, so none of it is going to be cleared from the blood. But in this case, none of it got reabsorbed, so all of it made it into the cup. Means 125 of it got cleared from the blood because none of it went into the blood. It's a few we got like a number for another substance, substance X. So we get substance X right here. Let's say substance X was at 65. We started out with 125. Now we got 65 for our clearance number. That means 65 milliliters per minute was cleared from the plasma. That means the other, let's just say 100. Say we put in 100, 65 of it got cleared, got put in the cup, cleared from the plasma. That means 35 of it got reabsorbed into the blood. Let's say we got like a higher number. So we put 100, then we got out, we got 150. That's higher than what we even put in. So that way we know, okay, it went through, none of it got reabsorbed because we have more. So that means some must got secreted from the blood into the tubule even more down the road. So that's what we ended up with more. Let's see, where do I want to talk about this? I think we can talk about it here. I think we're ready for it. Another important thing, especially with talking with glucose, is something called threshold. And threshold's important because, especially for glucose, it's gonna have channels. We'll just say right here in the proximal convoluted tubule. There's gonna be specific glucose channels, and they're called GLUT2 channels, and those help push glucose into the blood. There's also another channel, which one is it? It's the SGLT channel and the GLUT2. Pretty much the SLGT is what pulls the glucose from the tubule into the cell. Then from the cell, the GLUT2 takes glucose within the cell and pushes it out into the blood. And so in a healthy individual, 100% of the glucose is going to be, that's going to be absorbed, that's going to be filtered. 100% of that filtered glucose is going to be pushed back into the blood, and none of it's going to make it down here. But someone who's like diabetic and they have way too much glucose in their blood, they're going to have so much glucose being filtered in here, so much more than what it's used to, that these channels are going to become saturated, and they're just going to be like cramming in there, but there's going to be so much that the channel can only do so much at a time, that there's going to be ones that aren't going to make it into the channel. They're going to pretty much not going to be able to find their way in, and then they're going to leak, because ones are trying to get in here, but there's so many trying to get in, some of them are going to make it, so they're going to make their way down here past their opportunity to be reabsorbed in the proximal convoluted tubule. And then they're not going to get reabsorbed again, and so they end up making it into our P cup. And then we get a measurement of glucose in our P. And at that point, we know the person has something not working, because you should never have glucose in the P. But if they do, you know, they probably have something going on, probably have diabetes. And this can happen with other things too. Other channels can get oversaturated or saturated, and they're just not going to be able to keep up, and it's just going to be secreted. But yeah, that's saturation. That's probably the most important one for it. That's all we really talked about in class with glucose. So you should never have a clearance number higher than 0. Should always be 0, because 0 of it should be cleared from the blood. All of it should be reabsorbed. Let's see here. Yeah, clearance, talked about GFR, talked about threshold. I guess we didn't, did I say threshold for it? So it has its threshold. Glucose has its threshold within the blood. I think that within the blood, I think the healthy range of glucose in the blood is like 60 to like 180, about. But like in a diabetic, like I said, if they have high amounts of glucose in the blood and it's just getting filtered through and it's way too much, those channels aren't keeping up, they're probably gonna have something more like, I think like the threshold was like 200 or 250. We'll just say 250 for now. But if they have 250, like whatever, milligrams per milliliter or whatever that measurement is, if they have like 250, 250 plus, like 250 is the threshold. If they have like less than that, they're gonna be okay. They're gonna be able to, channels are gonna keep up. But once they hit threshold and it's above 250, can't remember if it's 200 or 250, it was somewhere around there. If it's above that, it's not gonna keep up, and that's when problems are gonna occur. So that's threshold. This is a lot of stuff. This is crazy. Okay. So yeah, that's that stuff. I know I could have explained it better, but not quite there yet. Need to keep learning it. But this is another good part right here. Kind of exciting. Whew. Okay. So we talked about the filter. But let's talk about what makes up that filter, what that filter is. So we know the filter is filtering stuff from the capillary. We know I have a pressure coming from the capillary, it's pushing stuff out of the capillary, but not everything's gonna make it through. We know we have a filter that's filtering it and letting it come into the Bowman's capsule. But there's a membrane, and that's our filter. Let's just draw it right here because I think this is a little too crazy. So we have Bowman's capsule. Erase this stuff. Sorry. We have the glomerular capillaries. It's a little too much. Draw this a little bit lower. And we have Bowman's capsule going down into the tubule. And okay. So our first line of defense, our first filter, is called the fenestrated membrane. Something fenestrated, I can't remember the word, but it's fenestrated. And so the fenestrated, it's about 70 nanometers. That's how wide it is. That's the space that's letting stuff filter through. And the reason why this number is important is because that's the largest filter, part of the filter, and red blood cells are, I think, 700 nanometers. And so there's no way in a healthy individual, if they have this about 70 nanometers, that we're gonna find blood in the urine. But if we do find blood in the urine, we know something's wrong, because if this is the biggest filter and blood's coming through, we know something's not right if we have blood in the urine, so we shouldn't. But yeah, red blood cells is like 700 nanometers. So first, yeah, we have the fenestrated layer. Can't remember the word for it. But then we have something called the basement membrane, like that. That's even smaller. I can't remember the number, but it's smaller than 70. And so that's even filtering things even more. And then we have these things called podocytes. I think it is. I took a picture of it just so I can make sure I'm not doing it wrong. Podocytes. And it's the fenestrated endothelium. That's what it is. Okay. Then we talked about the basement membrane. Now we're going to talk about podocytes. And let me check my battery to make sure this thing's not going to die. Oh, we're still good. Okay. So, then we have these podocytes. And these things aren't exactly made for filtration. They have another purpose. They do aid in filtration. So what these guys do is, one of the things they do is let's say this eraser is the glomerulus. We talked about there's like a 50 millimeters of mercury of hydrostatic pressure. That's a lot for that, for those capillaries. And so you have these podocytes that kind of wrap around the glomerulus like this, and they kind of just help secure it and kind of give some support for all that pressure, so those don't burst. So that's one of their that's one of the things they do. But also they help with filtrating, because as they wrap around, they block things off a little bit, but they also have openings. And their last one, if I can remember what it was, I honestly don't think I can. Filtration slits, net-like filter. So then we have these filtration slits, and these are supposed to be in between the podocytes, or pedocytes. And they're kind of like that last smallest filter. But yeah, that's what the filter is. And like we talked about it being freely filtered. We talked about being small, no charge. So things like that fit that category are going to be able to be filtered through here. And we talked about, like, glucose was one of them. The other one is inulin. There's tons of other things that can make it through there. But something like red blood cells, we don't want that inside. So that's why our biggest one is 70, and that's way too small for a red blood cell to fit through. But yeah, kind of back on this pressure topic, there's something called auto-regulation, because we're gonna talk about GFR right now. So if we have a high blood pressure, it means we have lots of blood, just like a high blood pressure in our body. We're having lots of blood come through our vessels and making it down into our arterioles. And if there's a high blood pressure in there, it's gonna create a high pressure within the glomerulus. And that high pressure is going to increase our net filtration rate, which was 10. If you remember, we added these up, and the net filtration rate was 10. But if we have a high blood pressure, that's what that hydrostatic pressure is based off of, or the high blood pressure. That's going to increase hydrostatic pressure, which is going to then increase net filtration pressure. And if that's the case, that's going to increase GFR. So if we have more pressure, more fluid's going to be pushed out. So that's going to increase GFR. And that's not good, because we don't want an unhealthy high rate of GFR. So that's why we have auto-regulation. But also, if we have like a low blood pressure and it's causing low hydrostatic pressure, it's going to cause a low GFR. And that means we're not having enough, not a high enough GFR, not a high enough glomerular filtration rate. So our body has a way of regulating this, and it has its own way of doing this without the autonomic nervous system. And one of the ways it does it is called myogenic. And what that does is, with the smooth muscle, the arteriole, if there's high pressure on the arteriole, so we have high blood pressure, it's expanding those, high GFR, it's not good, but within the smooth muscle, the arteriole, it's getting pushed because of high pressure, it's getting pushed out, and that's going to open up stretch-activated calcium channels. And those stretch-activated calcium channels are going to release calcium, which is going to cause that arteriole, that smooth muscle, to constrict down lower. And as it constricts down lower, we have a smaller diameter, and that's going to cause less blood to come through the afferent arteriole. And less blood inside of the glomerulus is going to cause less pressure, which is then going to bring down our blood flow. It's going to bring down the pressure, which is going to bring it to a normal GFR and get us down to a normal net filtration rate or net pressure. So myogenic can really respond if there's a high blood pressure. But there's another thing called tubuloglomerular feedback. And this one's cool because this one involves something called the macula densa. We talked about it over here. That's the thing that's in between the, it's like the first part of the late distal tubule. And this one's cool because it has a way of, what's the word I want to use? It has a way of monitoring sodium. I think it's just sodium. I think it's something else. Is that written down somewhere? I don't know. But it monitors like sodium. It might be something else too. But it monitors the sodium in the blood. Right around, somewhere around right here with the filtration. If there's high amounts of sodium, it knows that it's like a high blood pressure. But if there's a low amount of sodium, it's like a low blood pressure, or I can use that with like a high GFR or a low GFR. But in this case, let's say it's a low blood pressure. So that low blood pressure is causing low hydrostatic pressure, which is decreasing the net filtration pressure. So less stuff being filtered out, decreases the GFR. That decreases the NaCl filtrate. And then macula densa senses that and says, okay, there's less NaCl, there must be a low GFR right now. And so the macula densa is going to go into release nitric acid, and nitric acid is then going to dilate the afferent arteriole. It's going to open it up more, open up that diameter, which is going to allow more blood flow, more blood to come through and flow into the glomerulus, which is then going to increase the pressure, which will increase the net filtration pressure, which will then increase GFR to where I want it. The opposite can happen where we have high blood pressure, high hydrostatic pressure, and high GFR. High GFR, the macula densa is monitoring. It monitors high NaCl being filtrated through, and it's going to know that's not good because it's too high of a GFR, too high of a hydrostatic pressure, high blood pressure, and it's then going to release adenosine, which adenosine is normally I think it's normally a vasodilator. No, it's normally a Wait a second. Trying to remember here. So we have we're talking about high blood pressure. So adenosine is usually a vasodilator. But in this case, within the kidney, it's a vasoconstrictor. And so if we have high GFR, high pressure in here, the adenosine released from the macula densa is going to constrict the afferent arteriole. It's going to make it smaller, which is going to allow less blood to come through. That's going to decrease the pressure, which will decrease the filtration rate. So it kind of acts in accordance with the myogenic. Another cool thing about that, we'll talk about it more over there. We'll just jump into it right now because we're right on with it. So that's a way the pressure can be, or I guess we have high or low blood pressure. Obviously we talked about how it's going to affect the GFR, which is going to affect the flow within the kidney, what's being filtered through. We need that as a healthy range. And so there's another system, and this is more to do, like this we talked about was to do with autoregulation, intrinsic. This is happening within the adrenal medulla, and the kidney's kind of taking care of itself. But if the kidney can't really keep up and keep its harness on this thing, it's going to tap into the the Ross system, which is, I can't remember the name. It's the renin, angiotensin, aldosterone system. And so, let me see where I want to start. Okay. It's kind of like what we were talking about before. We have low blood pressure, and that's going to create a low GFR, low glomerular filtration rate. So we're not having enough stuff getting filtered through. And there's a part on the juxtamedular, and I guess, let's see. There's the macula densa, and also, yes, the macula densa senses that, but then the juxtamedular is going to release renin within the kidney. And as it releases renin, it's going to get put into the blood, and as it gets put into the blood, it's going to react with angiotensin, and renin plus angiotensin is going to give us angiotensin 1. And angiotensin 1 is going to react with ACE from the lungs, and that's going to react, and it's going to become angiotensin 2. And this is the thing that really comes to the rescue in a situation like this. So, continuing this, angiotensin 2 then is going to raise the blood pressure, which is going to raise the GRF, or put it back to a normal, a healthy range. Let me see. I want to push this back a little bit. Seems good enough. Okay. So, talked about angiotensin 2. This is the playmaker right here. Angiotensin 2, what is it going to do? It's going to, number one, it's going to cause the brain to, something in the hypothalamus is going to increase thirst. Because remember, we have low blood pressure right now, and we're trying to fix that because it's causing a low GFR. And so, since we have this, if we increase thirst, we're going to increase water intake, which is then going to increase our blood pressure, because our blood's made of plasma, has plasma, which is mostly water. So as we intake more water, it's going to increase the volume of our blood, which is going to give us a higher blood pressure because there's more blood within those vessels. It's also going to release ADH. ADH, something called osmoreceptor and a baroreceptor. Osmoreceptor, I'm trying to remember what it was, I just read about it today. Osmoreceptor is within the brain, and it has like these vessels, I can't remember exactly what they are, but in times of when the body is dehydrated, those vessels lose water because there's a higher concentration of solute within like the blood and the body, and so the water is going to leave and go to those areas of high solute concentration. So these vessels are going to lose water and they're going to shrink. And as they shrink, they send off action potentials that trigger the brain to release ADH. And ADH is important. We're going to talk about it down here, but ADH reacts with a cell within the collecting duct to open or release aquaporins, to open these channels to reabsorb water, to bring it back into the blood. So that's why ADH is important. The baroreceptors, I'm trying to remember. Yeah, the baroreceptors we talked about a couple units ago within the corticoid, I think it was called. And then it was also within a part that branches off of the heart, the aortic arch. And those sense blood pressure because if they're stretched, it's a high blood pressure, but if they're not stretched, they're sending less action potentials, and those less action potentials are going to release ADH, which are going to react to that cell to open up more aquaporins to bring in, reabsorb more water back into the body. And that's also with thirst, more water, higher blood pressure rate. It brings blood pressure back up, helps with it. Another thing you can do, the adrenal gland, it's going to release aldosterone. That's the second A. Aldosterone in the adrenal gland is going to increase the activity of the sodium-potassium pump. And within a cell in the kidney, if the sodium-potassium pump is activated, that's going to take sodium from the tubule or from the lumen, and it's going to pump that, or I guess it's in the cell. We're going to have sodium within the cell, but it's going to come from the lumen or from the tubule, and that sodium in the cell is going to be pumped out by the sodium-potassium pump into the blood. So if we're increasing the sodium-potassium pump, we're having more sodium pumped into the blood. And we know water is going to follow salt, and so or follow sodium. So when sodium gets pumped in the blood, water is going to follow, get more reabsorbed. It's going to bring water into the blood vessels, which is going to help bring back the blood pressure back up. Third thing is the systemic arterioles are going to vasoconstrict. I can't remember exactly where that's from. Maybe from, I don't know, like adrenaline or something. Norepinephrine, epinephrine. Either way, the arterioles are just going to constrict, which they're going to constrict. It's going to help raise the blood pressure because it's making a smaller area. Number 4, vasoconstriction of the efferent arteriole. So over there we talked about with the autoregulation, it was more just focused on the afferent arteriole. If we had a low blood pressure, which was causing a low hydrostatic pressure, which was causing a low GFR, we could just dilate that afferent arteriole to let more blood in, which would increase the pressure within the within the glomerulus. If we got a high blood pressure, we're having too much, we could just constrict that afferent arteriole, which would reduce the amount of blood coming in. That's something I kind of forgot to mention. Actually, I want to go back to it because at first when I was learning it in class, it really kind of threw me off because I was like, what? Because I was thinking, I was like, okay, if we're going to constrict, that should raise blood pressure, but you're saying that's going to lower blood pressure? But really it's just going to lower blood flow like we have here. So if we're going to vasoconstrict that afferent arteriole, we're going to make it smaller. And so it's going to increase like the blood pressure right here in this area because it's constricted. I'm looking at the wrong part. The afferent arteriole, if we constrict it, it's going to reduce the amount of blood flow in here, which is going to reduce the amount of blood, which isn't going to make it so stretched out. So it's going to make it be able to be smaller, less pressure. And so this is pretty much like in reference to the glomerulus when we're talking about constriction. We're talking about constriction of the afferent arteriole, but we're talking about how it affects the pressure within the glomerulus, not within like the vessels of the body. Because usually if you think of vasoconstriction, that's going to increase pressure in the blood, in that vessel, but if we vasoconstrict here, less blood flow in here, which is going to decrease the pressure within the glomerulus. So that's something that threw me off in class, but then once I got it clarified, it helped quite a bit. Okay. Yeah, back to the vasoconstriction. So we talked about, most of the time over here with the autoregulation, it's more having to do with the afferent arteriole, either constricting it to reduce blood flow, to reduce blood in the glomerulus, which is going to decrease the pressure. But if we wanted to increase the pressure, we would dilate it to allow more blood flow in there to create more of a pressure within the glomerulus. But with this one, what it's going to do, because this is for low blood pressure, so, or I guess it's more low GFR. So if we have low GFR within the glomerulus, having less stuff being filtered through. So what this is going to do, I'm pretty sure the angiotensin, I don't know if it directly or sets off kind of a domino effect, but it's going to send something to an A1 receptor on the efferent arteriole to vasoconstrict. And we have the glomerulus, kind of ugly drawing of one, but it's fine. We have our tubule. Barely see it, it's okay. We have blood coming from this way, from the afferent, entering here, blood. When we have a low GFR, we want to increase the pressure in here. This is saying, oh, we can just constrict this down so it gets smaller, and it's going to stop, it's going to let less blood through. It's going to kind of create a backup of blood, and that's going to increase the blood volume within the glomerulus, which is going to bring the pressure back up, bring the GFR back up. And this was angiotensin 2. There's something else. Oh, I wish I had it, but there's another thing that can happen where release of renin, but then like something, instead of ACE, I think ACE2 gets released, because it's like the opposite effect. If there was like high blood pressure and we're trying to bring it down, it's like ACE2 would get released and react with angiotensin 1. And I'm trying to remember, but I think we would like release angiotensin 1 through 7 is what it's called. And angiotensin 1 through 7 is going to have the exact opposite effect of all these. So instead it's going to not create thirst. It's not going to release ADH for water reabsorption. It's going to let the water be excreted out. It's going to decrease the activity of the sodium-potassium pump, bringing less sodium into the blood, keeping more sodium into the tubules of the kidney, so more water stays with the salt in the tubules to get excreted. It's going to vasodilate the systemic arteries, make them bigger. It's going to lower the blood pressure. For this one, it probably just won't. Maybe it can dilate the efferent arteriole, but it's definitely not going to constrict it. And it's just going to try to decrease the blood pressure in there. Okay, we're almost done, thank goodness. It's absolute craziness. Okay, I have to do this section by section because I have a lot of these bad boys. Okay. Hopefully we can get this done quick. Okay, I need to memorize these more. But proximal convoluted tubule. Remember, that's the first section we talked about coming off of the Bowman's capsule. So this guy is important because this is where most of our water reabsorption is going to happen. It's going to have these aquaporins. That's going to let water through directly through the cell. It's also going to let water through paracellularly between the cells. I kind of like to break down all of these channels because it's just so much. And so the first one I want to talk about, let's just think about, okay, glucose. Okay, glucose is going to be let in. Okay, sodium is a super important player here because it's going to help with secondary transport. It can either be a symporter with bringing molecules in or out, or it's going to be an antiporter where it comes in and lets something out, or it goes out and brings something in. So this is very dependent on sodium. Sodium is going to drive a lot of these channels. So in this case, let's start with water. Water's going through that way. Another important thing with water is as it goes in the proximal convoluted tubule, as it goes in between cells, it can also give a ride to calcium and potassium and bring them into the blood. This is a blood vessel right here. The reason why this is important, this is like the lumen, or like the tubule right here. And so stuff's being brought out of the tubule into the cell, then brought out of the cell into the blood, or it's being taken from the blood into the cell, into the tubule. But in this case, we're having a lot of just reabsorption, because it just got filtered, it's making its way through, stuff's getting put back into the blood. So we have this SGLT, glucose, sodium comes in, brings in glucose. Glucose can then leave through this GLUT2 channel and enter into the blood. 100% of glucose should do that. We have another channel, kind of similar. It's a sodium one that brings in lactate, or it can also bring in an amino acid. Brings those in, and there's another channel over here where instead of sodium coming in with it, sodium is going to come in and then let it out, or lactate, or amino acid. Now we're ready to talk about, well, also there's a sodium-potassium pump. Like we talked about, sodium's a huge player to drive this, and so it's going to let sodium out, 3 sodiums out, 2 calciums in. That's just our classic, most important sodium-potassium pump, most important thing in the whole wide world. And it's going to create a gradient for sodium to do what it does here, to be awesome. So now we're going to talk about something called carbonic anhydrase. And it's inside the cell and it's outside the cell. What's going to happen here is we're going to have this pump right here that's going to pump hydrogen out while it's bringing a sodium in. So that sodium is going to allow for that hydrogen to come out. We're going to have hydrogen out here, and it's going to combine with carbonic acid, and it's going to go through the carbonic anhydrase, and it's going to become water and CO2. And then it's just going to diffuse through into the blood if it wants to. Or it can diffuse into the cell, and inside of the cell, it's going to be water and CO2 as it diffused in. It's going to go through the carbonic anhydrase. And like here, it's going to do the opposite. It's going to become a hydrogen and a carbonic acid. Hydrogen, like I said, it's going to go over here, be pushed out, kind of go through the cycle again. But carbonic anhydrase is going to go through out this way, and it's going to go out with the sodium. The sodium is going to drive it out. Okay, I covered everything for that one. That's our biggest one. It's crazy, but I'm glad to be done with it. Proximal straight also brings water out straight through the cell, paracellular, through between cells. This one's cool because it has to do with a acid and base, and acid and a conjugate base, I guess I would say. And still has sodium potassium pump on every single one. It's so important. But in this case right here, we're going to start out with, we have a acid in the cell. It's going to get broken up into its acid and its conjugate base. Or hydrogen, its conjugate base. Conjugate base is going to be pushed out, and it's going to be driven with the force of a chloride coming in. Chloride comes in. Conjugate base out. Like we saw before, hydrogen is going to be driven out with the coming in of nitrogen. Nope. Sodium. They're both going to be out here. They're going to come back together and become their acid. And it's just going to diffuse all by itself through and go through that cycle. But what's important here is we have fluoride coming in. So I guess maybe you could even say this conjugate base is the driving force for this chloride. So chloride can come through, and then leave through either a CFTR channel, or it can leave through a CL channel that's also being driven with a potassium. But this CFTR channel is important because people with cystic fibrosis, I think it is, don't have this channel working. And I can't remember 100% why that's important, but it's something to do with the gradient of CL you need in the blood. I think it contributes to salt, but people without that channel are going to have cystic fibrosis. Okay, easy one right here. Descending tubule, still soluble to water. Sodium potassium pump on every single one because it's so important. So important for that gradient. Okay. Now we're to the ascending tubule. We just passed the loop of Henle. Now we're going up. Now we're not letting water through anymore. Water is getting blocked off. It's not permeable to water. Descending was permeable to water, but not really permeable to solutes, permeable to water. Ascending, not permeable to water, but permeable to solutes. That's going to be important in just a sec. Has this channel that's going to let in sodium, potassium, and 2 chlorides coming in. Sodium's getting pumped out through the sodium-potassium pump. Chloride's getting pumped out, or not pumped out, it's just leaking through this channel. And potassium is just leaking through this channel into the blood. Super important. Descending tubule, soluble to water, not to solutes. Ascending tubule, not soluble to water, but soluble to solutes. Then we get to the macula densa. Macula densa we talked a lot about. Not solvent to water, but what it does do, lets in sodium chloride. If you remember, we talked about how the macula densa monitors sodium chloride that's being filtered through. Not a lot of sodium chloride. It gets worried and says, hey, we have a low GFR. Lots of sodium chloride says, hey, we have a high GFR. We need to do something to fix it. And that's where it can release nitric acid. It can release adenosine to constrict. Nitric acid was to dilate. And also, it can help with ROS, which the juxtamedullary releases renin. Those two are kind of buddies. But important, lets in NaCl, sodium chloride, lets them out. Sodium potassium pump, sodium leaves, potassium comes in, potassium can leave through this leak channel, chloride can leave through this channel, sodium can leave through the sodium potassium pump. But remember, that's important to autoregulation. Oh, another important thing here, if we were to give a diuretic, we would block this channel, or block a lot of those channels, so little sodium chloride is coming into the blood. We have little sodium chloride coming into the blood, we have more in the tubules, the tubule. More salt in the tubule means water is going to follow that, and water is going to stay in the tubule, and we're going to pee more. It's going to get rid of fluids. Now we're on to the late distal. This is a cool one. Text. Okay, this late distal collecting tubule one is cool. Probably my favorite. And the type A, type Bs are pretty cool too. But the late tubule, This is good for our drawing. Remember we had ascending or descending, ascending, distal, collecting tubule. Kind of like distal, collecting tubule right here. And bring that down a little bit. The reason why this one's cool is because this is kind of our last chance to reabsorb or not reabsorb water. And so we talked about ADH over here with the brain. If we have low blood pressure or low GFR, we're going to release ADH to the brain through the osmoreceptors and the baroreceptors. And ADH, let's first talk about if it doesn't get released. No ADH, it's not going to activate this G protein. This G protein, if it's activated, it's going to activate this vesicle that's full of aquaporins. I'm getting a little carried away. No ADH, all this is doing is letting sodium in through these little channels, potassium's leaving out, potassium can leave out this way to the blood, sodium potassium pump's going, so sodium's coming in here, sodium can leave here, potassium come through here, leave out. It's very simple. That's without the activation of ADH. We have this potential vesicle that has aquaporins in it, but it's not activated. But if we release ADH from the brain due to low blood pressure or low glomerular filtration rate or hydrostatic pressure within the glomerulus, we're going to need more water to help raise the blood pressure, bring the blood pressure back to normal. So ADH is going to get released. It's going to activate this G protein. Can't remember exactly what the details of it, but it's going to activate this vesicle. It's going to open up and let aquaporins out. Aquaporins are going to go to the membrane and open up aquaporins on each side. What this is going to do, in the tubule we have water. Now tubule is opened. Water is going to be able to come through these aquaporins into the cell, into the blood. Therefore, bringing more water back into the blood. If we have more water in the blood, it's going to increase the volume of blood, help increase the blood pressure, which will then go and help increase GFR, which will help make us happy. Super cool. And we'll just jump onto this right here because this is why I drew this thing. Oh. Sometimes I like to think that I'm a handsome guy. Okay, so this is osmolar right here. This is an osmolar measurement. 100, 300, 600, 900, 1200. This is like a concentration, osmolar concentration. And this is a juxtamedullary one. What are they called? Cortical one. Cortical nephron. Remember the loop of Henle doesn't go, the loop, descending tubule and ascending tubule, they meet up around right here. They don't go so far down, but I just drew it for this one. So in a normal one, just know, it just goes to about right here in a cortical one. But this is a juxtamedullary nephron. But what's cool about this is we have the fluid within the tubule moving down the descending, which is soluble to water. Loop of Henry, start going back up, not soluble to water anymore, but we're soluble to solutes. That's when I was like over here and I was talking about how this is really important. It's gonna be important in a minute. This is the minute I was talking about. Moving through, and it just gets filtered out, let's just say. We'll talk about these in a second, but first let's talk about these solutes. Then we have blood. Blood's moving in the opposite direction. Blood's coming in this way to the afferent arteriole, juxtamedullary, back, or not back, but out the efferent tubule, moving against the flow of the tubule, they're not like interlinked, but they're just like, this guy's moving this way while this guy's moving this way. And they're just moving in the opposite direction right by each other. But at this time, we're talking about the whole time, there's the tubule and there's the blood vessel and there's cells. Things are being transported between the tubule to the cell. So it's like blood's going this way, and I don't really want to use blue for this because it's not water. So blood's going this way, in this direction, and the tubules, still recording hopefully. Okay, we're still got 10% left. So tubule fluid's going that way, blood's going this way. Right here, blood's going this way, tubular fluid's going that way. Over here, blood's going that way, tubular fluid's going that way. Blood, boom, opposite because it's flipped. But the important thing here is to pay attention to these, this side's solvent, soluble to water, soluble to solvents. So what's happening is, let's just talk about the tubule. Tubule comes out, it's like at 300. Water is moving out. Water is going away. So it's losing, the osmolarity is going up. And as you see, it's going up 100, 300, 600. Water's going away, water's moving out. We're just left with a high concentration, high osmolar concentration of solutes. Now we're at 1200, and this is part of because there's urea down here. But then we start coming up. And what happens? Solutes start becoming soluble. Solutes are leaving. Oh, solutes are leaving now. So now our concentration is going up because solutes are leaving. Now we're back up to 100. The blood is like right here. Remember, these solutes were leaving. Where are they leaving to? From the tubule, they're leaving into the blood. Blood's right here, blood's at 100. Blood's coming down. Oh, solutes were leaving tubule and they're entering the blood. Blood concentrations, oh, it's going up, it's going up, it's going up, it's going up. We're at 1200. Urea down here is what makes it so high. If we were talking about the cortical one, it'd just stop here at 600, but here we have urea. But we're super high because we had a bunch of these solutes come in from this soluble membrane of solutes. Then we start coming back up. And remember what's happening right here? When we're moving down the tubule, water is leaving the tubule into the blood. But now we're coming up, now the blood's perspective. Blood's getting water now. We're getting water, getting water, getting water. That osmolarity is going down because we're having more water come in. There's less solvents per liter. Osmolarity going up, going up, going up, going up in the blood. So that's pretty cool. I didn't understand that until I was drawing this today. So it is pretty neat. Okay. So that's how that works. And again, it's just this much for the juxtamedullary at 1200, a super high osmolarity. That's because down here, it's something to do with the urea. I can't remember why, but for some reason the urea makes it really high in this lower region for the juxtamedullary. For the cortical one, cortical nephron, or whatever it is, it stops like right here, and it just goes down to like 600. But still the exact same thing's happening, but it just goes to 600 because it's not affected by the urea. But here, back to these cool ones, the late distal one is, if we need to, like we're talking about, if like with low blood pressure, and we need to do like a last ditch effort to bring blood back in, sorry, not blood, but water back in, then we're gonna open up this guy with the aquaporins, and then, because usually this is, I'm just gonna use black, but usually this is not soluble to water. Not soluble to water, usually, when it's not in the activated state. But then if we're in low blood pressure and we need water, ADH is gonna come from the brain, open up, activate the GE protein, open up the aquaporins, and then now, since we have aquaporins, this becomes soluble to water. And right here, I'm not gonna draw it perfectly, but we have the blood. So now the aquaporins are open, water is able to leave the tubule and enter back into the blood, and it's gonna help raise blood pressure. And yeah, blood osmolarity as well. But yeah, it's gonna help raise, that's how that plays into, if you're looking at it like an nephron. Okay, this is the very last thing and then we're done. I'm so excited because I can go home. Okay. Let me see what I might have to really hurry. Okay, we still have 9%. Accidentally swiped out. But we're still good, we have 9%. So this is a really cool part right here. This helps with balance of pH within the body. I'm honestly so brain dead right now, I can't remember where these cells are found. I can't remember exactly within the tubules they're found, whether it's like the proximal or the distal or the late distal or the collecting or what. But what really is cool what happens here, first we're gonna talk about pH. Normal pH for human, I think, is at 7.4. That's like the healthy, that's where you wanna be. Probably a little bit of variance, but really not much. But if we're higher than that, we become basic, alkalosis. Hello. Okay, I'll be down in just a couple minutes. It's up to you, whatever you want to do. You find to come up if you want. What? Yeah. Okay, I'm just gonna finish my video real quick. I love you. Here, a really cool thing is we have this type A intercalated cell and a type B intercalated cell. And we talked about blood pH. If we're higher than 7.4, we're basic or an alkalosis. If we're below, we're acidic or an acidosis. And so for type A, if you think of it as K, type A, we're in acidosis. Our blood is acidic. So type A is what we're gonna turn on to rescue us from that. So we're back to carbonic anhydrase. High acidity in the blood. What are we gonna do? CO2H2O, we talked about before, is gonna diffuse. This time it's gonna diffuse from the blood, come inside the cell. It's gonna go through carbonic anhydrase, become a hydrogen, and the conjugate base, which is bicarbonate. And what's gonna happen is, which is cool, is bicarbonate, which is more basic, which is a base, it's gonna come, the Cl is gonna come in, and it's gonna let bicarbonate in. And as bicarbonate enters the blood, it's gonna bring the blood pH up because we're getting something more in that's more basic. So it's gonna bring the pH back up to our normal level. But then the H, which is, what's it called? It's more acidic. It's gonna get pumped out through an ATP pump with the potassium. And then it's going to get, also can be pumped out through an ATP pump for just hydrogen. But either way, hydrogen is gonna get pumped out. It's gonna put into the tubule, and it's gonna be in the lumen tubule. It's gonna get excreted. We're gonna get rid of it. That's just if we have acidic blood. But also with this too, another important thing to see is when we're fixing this, kind of a consequence is, what do we have to do to get the hydrogen out? We had to use a potassium. Potassium is going to come in the cell, build up potassium because we're pushing hydrogens out. Potassium is going to come into the blood through a leak channel. And it's going to create a high amount of potassium in the blood, which leads to hyperkalemia. But it's going to bring our pH up. Type B, we have basic blood. It's the exact same as this, but just flipped. We're still going to have CO2, H2O diffuse in. It's going to go through carbonic anhydrase, and then this time the H is going to be on this side, and it's gonna get pumped through the very same cells or the pumps over here, ATP by itself, H plus is coming in, or ATP with a potassium coming in and a hydrogen or H plus coming in, potassium going out. Hydrogen is gonna get pumped in. Now we're putting in more hydrogens, or basic, we're putting in more hydrogens, more acidic, it's gonna bring us back down to a normal pH. But with this, the bicarbonate conjugate base is going to be pumped out with a antiporter of chloride. And I forgot to draw it. Did I? Oh yeah, but then then the potassium that came in is going to be pumped out. We're pumping potassium out of the blood to bring the hydrogens in. So that's going to lead to hypocalcemia. So that's how in alkalosis it leads to hypokalemia, and in acidosis it leads to hyperkalemia. It's through these intercalated type A and type B cells. That's everything. We got through it, we did it. My wife is here to witness it. And we just finished essay question number 1 for Unit 4.